Alright, so now we come to home plug. And this is one of my favorite because I have bought home plug right from day one, 2000, and I have kind of both of them, one, AV, AV2, and so on and so forth. So it has gone through several generations, and this is what it looks like. You just buy 2 of them, or you can buy 4 of them, it doesn't matter, but minimum is 2. You buy 2 of them, put it in one room, and connect it to the internet, and then go to anywhere in your house, plug it in, and you got the internet in that room. So you don't need to wire, you don't need to wireless, and it is better than the wireless in many cases because wireless doesn't reach some rooms, whereas electricity does. Okay, so now, so basically, so that is actually the extender could be of 2 kinds. Wireless extension you can get by wireless itself, so you can buy an extender which will take the wireless signal and repeat it, or you could have an electrical extender which will take the wireless signal in this room and produce a wireless signal in the other room. Okay, so that is also possible today. The digital information actually is very easy to manage so that nobody saves anything. It's the analog which is difficult. So the signal comes, and then they could have a device, a router, or something else which will just divide it to people as they pay. So if you don't pay, you don't get anything. So one more thing, let me tell you, is that it's not that since you are getting electricity, you are going to get the signal. They would have taken off the signal before you get the electricity, first of all, right? And that was BPL, that was broadband over power line. Now I have finished that topic. I am talking about the home plug. So I switched, but I kind of didn't explain it very well. This is not for the broadband over power line. This is for internet inside your house. So distributing internet inside your house. So then nothing to do with the DSL. I have, for example, a DSL from AT&T. I mean, not DSL, I have UVerse from AT&T. And then I use this home plug inside the home to go from one room to the next. So this is totally orthogonal to BPL. So in the United States, we don't have BPL. But everybody has home plug, and many people have home plug. And it doesn't cost that much, $30 for the 2. This can be used only if you have electricity, which I think everybody has everywhere in the United States. Huh?
Whenever you have electricity, you have it.
No, okay, it doesn't use electricity. So the thing is, okay, 2 things. First of all, it doesn't use batteries because it is connected to the plug where electricity is. If the electricity goes away, obviously there is no battery in it and it will die. So your question is correct. You can use it if there is electricity. If there is no electricity, you are in dark. I don't think you want internet at that time. You are worried about cold and heat and everything else. Yeah.
If you're like a large apartment building though, where you might share wiring, would it be possible that like you'd be broadcasting your network?
Okay. So this is no. The question is, if you are sharing, you can have your own, just like your base station, your wireless, you can have your own password. Exactly same thing applies here. So everything can be on the, so there could be more than one network on the same wire. But only, so for example, if suppose you are sharing an apartment with somebody but don't want to share your internet with them, you could put your own password and all your devices you plug in this room, that room, that room, they will be connected. Of course, if they come and physically connect it, you can't do anything. But they cannot put their devices cannot talk to your network. I mean, this is a very personal answer and very personal question. I am a wireless guy. However, I always preferred wired stuff, personally. So, you won't, I mean, like, I tried wireless mouse, wireless speakers, wireless this and that, Bluetooth, none of that. The thing is, I would rather have wired stuff for several reasons. Health is one of them, but just the reliability, in the sense that there is no interference, less interference. Let me just say less interference. So, now the question is, which will win? Now, if you ask somebody else, they will say just the opposite. So, this is not universally agreed. And also, it depends upon the house. If your house has, there are several houses, for example, in my house, I mean, at least I haven't tried recently, but the wireless signal doesn't go to the other end. It doesn't go to the garage. It doesn't go to the pool area and things like that, right? So, I don't know. So, I'm just saying that basically, so then I have to look for the alternatives. Right? Now, having said that, it is not that this goes to every place either. So, let me tell you where it doesn't go. So it doesn't go through the transformers. And therefore, it may not go to some rooms in your house which are not directly connected to the same electrical wire. So when you have different circuits, then it might go through some circuits, and I don't know how does it do that, but it may not go through some circuits. So you know, like they say, your mileage may vary. But it is worth trying, you know, for $30, you know, it's much cheaper than wireless. Now the good thing is that everything that you have in your home is generally electrically connected anyway. So if you have a refrigerator, if you have a air conditioner, if you have anything else, very few things that don't have electric connection. So they are already electrically connected to the internet if you wanted to, if they had this little chip inside them. Right? You don't need to buy anything, just, you know, so in future that is what will happen. Basically they will have this chip inside them, and so then you can connect to them by your computer. You just connect to the refrigerator. So home plug AV. So the home plug actually came out 1.0. Home plug is actually an association of industries, companies that got together, and there were other competing standards at the same time. So at the time when I first bought my home plug device, actually I had to be very careful that I don't buy a device from a competing standard. So, but all of them died. So home plug is now universal, almost like 95% they claim. So 5% are still alive. So 95% of the devices today are home plug of the electric power line devices. It says 90% here, so 90% must be correct. So how does it work? Basically they use the spectrum from 1.8 megahertz to 30 megahertz. That's roughly from 2 to 30 or 28 megahertz spectrum. Now this is a very simple thing. Now, and in wireless course we talk about in great detail as to what is hertz and how it is. But electricity is electromagnetic and wireless is electromagnetic. They are same philosophy, same principle, same everything. Alright? So basically you have 28 megahertz, and then you have to decide what modulation you use, how many bits per hertz you get, and that tells you how many bits you will get at the end. So we can get from 28 megahertz 20 to 200 megabits. Of course, why is different? Because it depends upon how much noise you have on those lines. And the noise comes from everything, including your radio, from your light, from your Wi-Fi. Everything is electromagnetic. Everything, you know, interferes with each other. Alright, so 20 to 200 megahertz. So basically if you get, let's say, 10 bits per hertz here, 28 megahertz, and you get 10 bits per hertz, how many megabits per second you will get with 28 megahertz? Not too much difficult mathematical calculation. 10 bits per hertz, 28 megahertz, 280 megabits. 10 times 28. If you do 2 bits per hertz, you get 56 megabits. No, you don't have to multiply this one by 200. You have to multiply hertz by whatever number I am giving you right now. So 28, whatever megahertz you have, and I am giving you how many bits per hertz you are getting, per hertz. Right? So you multiply by that and you get total megabits. Anyway, so 200 megabits is a lot. And you can watch several movies for that bandwidth, okay? Now, so that's why it's called AV. AV is audio visual. Basically, you can watch movies over the electrical wires. So OFDM is used with 1155 carriers. So basically they take this 28 megahertz, divide into 1155 little pipes. Each pipe is 24 kilohertz wide. Alright, again you can divide 28 by 11.55 and you will get 20, this one. And you get so many, and then you don't use all of them, you use 917 of them, because what we do in OFDM is we use some carrier just for measurement, just to see how much noise there is here, how much noise is here, how much noise is here. So you use lots of them for pilot. Those are pilots, those are measurements. And so 917 are used for data, and the rest is pilots. Adaptive bit loading. And basically, depending upon what the pilots tell you, you change the loading near it. So basically, adaptive bit loading means that you change the modulation. And the modulation is based upon the noise level and the multipath at that frequency. So you might use 2 bits per symbol or use 10 bits per symbol. When will you use 2 bits per symbol? Yeah, when there is a lot of noise, you will use 2 bits per symbol. When there is not enough noise, you will use 10 bits per symbol. So you can get, whatever you can get. And each receiver keeps a table of signal strength for each of the other receivers. So this is an n-squared problem. If there are n devices in your home, n devices means n of these plugs that you have put, each of them will remember that to plug 1, the noise is such, plug 2, the noise is such, for plug 3, this is noise, this is called a tone map. Tone map will tell you that at this frequency is so much noise, at this frequency is so much noise, at this frequency is so much noise. So each map is a table, and then I have n tables, n minus 1 table to be exact. Symbol, what is a symbol? Alright, you have to wait until the wireless class. But just to be simply explain you a little bit here is that when you send, you don't send one bit. What you do is you take 2 or 3 bits together and you send it. So for example, if you take 3 bits together, now you have 8 combinations. Each of them is called a symbol. Okay, so how will you send 001? This is the way I will send it. This is the amplitude, this is the phase. How will you send 010? This is another symbol. So that is a symbol. Symbol is the group of bits that are sent together. And then robust OFDM. Robust OFDM is where you transmit the same thing on 2 to 5 subcarriers. So if you go back to this subcarrier thing, you might send the same symbol here and here and here 3 times in parallel. That way you can be very sure that nothing will get wrong, right? So that is robust OFDM, robo. Now in this home plug AV, they just use only one pair. So there are generally 3 wires. Remember, your plug has 3 wires in it. One is a ground, one is a line, and one is neutral. Right? So they just use line and neutral, not the ground. 4 channel access priorities, and then the traffic is divided into 4 priorities, 0, 1, and 2, and 3. And then obviously highest priority will go first. MAC is similar to that of Wi-Fi. So as in Wi-Fi, basically we use carrier sense multiple access. So basically that means that you look at the wire. If somebody else is transmitting, you don't transmit. If nobody is transmitting, then you follow some rules. Now all devices part of the same trust domain form an AVLN. So what is a trust domain? So if you have a network of your own, that is one LAN, that is one AVLN. If somebody else has on the same wires their network, just like we talked about another apartment, they have their LAN, that is another AVLN. Alright, and you can have multiple AVLN. But each audio visual logical network is like is a LAN, and they basically share a key, membership key. So before you can talk to the manager, you have to have that key. And so who is the manager? So there is a central controller which could be elected. So it's not that you have to buy a special device to say, well, this is my controller. All of the plugs that you have bought can act as a controller, but then you elect one, which is the controller for that network. Just like a root. Alright, that is called CCO, central controller. The CCO transmits beacons. What is a beacon? So basically, just like this, if you have done Wi-Fi, then this all will sound like very trivial, because this is all what is done in Wi-Fi as well, and in all wireless networks. So the base station transmits a beacon, which means a signal, which says, okay, now this is the beginning of the cycle, and please, station number 5, you can do this, station number 7, you can do that. So there is a whole set of schedule there that, you can do this, that, and whatnot, right? And then it tells you how long, who can do what, and what is available for anybody to grab. So that is the beacon region, right there in the front. And then the time is divided into at least 2 parts. One is CSMA region, non-persistent. There is a persistent, there is a non-persistent, and then there is a what we call pre-scheduled. So let me explain that. Persistent means long term. So if you have a big file, you go to the controller and say, look, I have a big file and I need at least 10 seconds worth of transmission time. So it will say, okay, all right, you get 5 milliseconds, and you keep getting 5 milliseconds until your 10 seconds are over. So that is a persistent shared CSMA region. Non-persistent. So now this one is local CSMA. Is that basically this is the reason where you just go and grab it. Basically what you do is you wait for some time, and the higher priority people wait less, lower priority people wait longer. So if nobody uses in that time, then you go ahead, things like that. Okay, so that is contention based. And there are many of those slots you could have. Many stations could try one after another. So that's why I have shown non-persistent again. Then persistent, allocated. And then what happens is video. If you're going to watch a movie for an hour, the plug will tell the controller, look, I need, I have a video going through, and I need for whatever this time, and so it will allocate that you get 5 milliseconds every cycle. So that is persistent, allocated. You don't have to compete anything. That's your reserved for you. So all right, so let's see if we finished everything. SART best effort transmission uses non-persistent CSMA. Real-time traffic uses contention-free period, which is this last one. Now, before you do any of this transmission, contention-free, you have to figure out how much time you need. And the time cannot be figured out until you know what bandwidth you have. And so figure out how much bandwidth you have to send something to figure out how much noise there is. And then based upon that, that is called sounding out. So you sound out the destination and you say, okay, all right, I think I can get 10 megabits per second and I have 20 megabits per, whatever, so how much time I need. Okay, so they have all the layers. They have layer 3, 4, 5, 6, 7, all those things. I'm not talking about any of the other layers. We are talking here just the first two layers, physical and MAC. On the top of that, there will be other devices, protocols. All right, security. So each device has a key which is called network membership key, NMK. And when you buy a device, it already comes with the default NMK, just like 000 for Bluetooth, and nobody ever changes that. Right? So anybody can come and connect. And that is reason is because most people cannot connect to somebody else's house. Nobody can connect to my house electrical wiring because it is connected to the transformer anyway. And so I'm safe. I didn't change it, but really the good thing is to change it. So they provide, basically all of these plugs have Ethernet port anyway. You see this Ethernet. So you just connect to that one, this Ethernet port right there, connect to your computer, and you can change the keys. So basically first idea is that you change the keys, and then once you change the key, then basically only the devices that have the key will be able to get onto the network. Now there is another key which is called encryption key, and now there is another course I teach on network security, and I won't go in much detail there, but one of the things in the security is that you change your encryption key every few seconds. Understand that? So you don't just keep a key and then keep it for 2 years, because then in that time somebody can just solve all the problems, factorize everything, and get all the keys, answers, and everything else. So you don't use it for more than a few seconds. So this encryption key is different than the membership key. Membership key is for life, encryption key is for seconds, which is used to encrypt the data. So there are multiple networks on the same wires. The CCOs coordinate the transmission schedule so that they coordinate with each other. So for example, if there are two, they figure out, there's a whole protocol which says, okay, is there any other network on this wire? Somebody says, yeah, I am there. Then we say, okay, all right, you take half and I take half. Things like that. That was AV. Now there is AV2. If you go to Amazon now and you look for home plug, you will find that most of the devices are AV2, and they will be advertising 500 to 600 megabits. Basically, AV2 uses 1.256 gigabits per second at the physical layer and 600 megabits at the basically the application layer. So now you can watch a lot more movies, and you can transmit multiple HD video streams. And the good thing is that it is backward compatible, so you could have some this and that. Having said that, I think compatibility is still questionable. I have two devices, one from Cisco, they talk to Cisco. I have another device from Netgear, they talk to Netgear. So you're better off, sticking with a vendor. And not even skipping the generations, like AV1 to AV2, they may talk. If they are from the same company, they may not talk. Who knows? So So that's another thing, is that basically you want to keep the same generation. Compatible with the home plug devices on the same wire. Additional spectrum. How does it make 600 megabits suddenly from 200? Well, it does several things, 9 things which we have on the list. First thing, they just use more bandwidth. They use up to 86 megahertz. So that gives them total 84 megahertz compared to 28. And then they do something which again we go back into the wireless course and we talk in a lot more detail. First of all, they use MIMO. Now all of you know MIMO because you have seen these multiple antenna devices now. So what do you do on the wires? Well, you use multiple wires. Previously, I showed you this picture here. They use only line and the neutral. There are 3 wires. Now we use 2 wires. I mean basically 2 pairs. So we use 2 pairs. Line neutral, line ground or neutral ground. So you have 2 antennas that way, right? Beam forming. And you do bit loading for each transmitter. So on this wire you look at the noise and do exactly what it is, and on this wire you look at the noise, and there are different OFDMA modulations on those. Lower overhead. They have reduced the packet delimiter and the delay and the acts, etc., so that not that many acts are transmitted. Efficient notching. What is notching? Notching is when you get a noise in some place, you just don't use that part of the spectrum. Some part of the spectrum around the noise source, around the noise frequency, and that is called notching. Cutting out that part of the spectrum. Right? And previously there was a fixed notch size. Now they try to figure out how wide is this noise, and they notch efficiently. So they use as much of the usable part as possible. Repeating. So signal is remodulated and remodulated at intermediate devices. So if there are 5 hops to get there, the intermediate devices will listen to the signal and then retransmit it. So that becomes digital again. So analog signal becomes digital, and then again that is called repeating. Repeater means digital amplifier. Better coding. So now they go all the way up to 12 bits per hertz. And aggressive code rates. What is a code rate? Basically in wireless, whenever you transmit 4 bits, instead of 4 you always transmit 5, 6, 7, so that there is some kind of error detection, correction and all that. So your code might be half, means you transmit 2 bits but only use 1 of them for the data. Rest is redundant, right? So code rate is 8/9, means they will have just 1 bit extra for 8 bits. Power control. So when it is going long distance, they use higher power. When it is going short distance, they use lower power. Power save, and then everybody sleeps when they are not doing anything, which is most of the time anyway. So that way they are also green. All right. Basically, AV2 products are available right now. In fact, as I said, they are not very expensive, and they give you 500 megabits advertised. 600 is written here, but I saw advertisements of 500 on Amazon and so on and so forth. Anyway, so you can do lots of video on those, and the way they get that high bandwidth is by several things which we are going to talk about, but the biggest thing is having more spectrum. The previous version went from 2 to, anybody remembers 2 to what they went? 2 megahertz to what megahertz they went to make how much megahertz? Nobody remembers. Then basically 2 to 30, it was 28. Now they added another 56. So if you have this much megahertz, right there you have 2 or 3 times the previous capacity of 200 megabits. And then they added MIMO. Now this is another interesting concept. MIMO you all know in wireless, but how do you do it in the wired network? And this one they did by basically having 2 pairs rather than 1 pair. So you transmit on 2 different pairs and then combine the signal at the other end. Whereas in the wireless we have multiple antennas, and then we receive many different signals and we combine them. Here it is in wired signal. And so basically they use 2 pairs. One is between line and neutral. So actually there are total 3 pairs because there are 3 wires in a power line. And so if you make a pair, you have 3 pairs. And so you could use any 2 of those 3. Beam forming. is that basically for each transmitter you will have we already did before adaptive bit loading, but now we will have to do it specifically for each receiver as well. And so you just concentrate on that receiver, as opposed to having one kind of noise level for each receiver. You will have total maps for all the receivers, separate maps for all the receivers. Lower overhead, and this actually should probably not make any big difference compared to what we have done here. Is like they have factor of 2 or 3 in the bandwidth here and 2 in the MIMO and so on and so forth. This one is just reduce the header size and so on and so forth. Efficient notching, remove some particular part of the spectrum when there is a lot of noise there. Previously it was a fixed size, and now it is very efficiently done as to depending upon what the noise level is, they just reduce that much. So these are 5-10% range improvement. The last ones. Repeating, and the repeating is that the signal is repeated. Repeating means digitally amplified, means that you bring it back from analog domain to digital domain, make 0 and 1 bits and then transmit it again on the wire fresh, so that way it can go longer distances. Better coding, and so 12 bits per hertz. So we were talking about previously some 4, 5, 6, 8 bits. 12 bits per hertz can give you a lot, and so now with that, and then the code rate is 8 by 9. Code rate is how many bits you put extra for ECC and error correction and detection. So you just put 1 extra bit for each 8 bit. So the code rate becomes 8/9. Power control, and the transmission power is again just like the spectrum is managed, the power is also managed. The level of the signal is managed to each receiver so that it is optimal. And power save, that was another thing, is that the energy has to be saved. Even though there is plenty of energy at the power outlet, they want to make sure that the stations can sleep, because that is what they are doing most of the time. Like in my home, I have put those power plugs. I don't think I have used them in 2 years. So they could be in a room ready to use, but people don't use them, and so it's better they're sleeping than awake.